Today we'll use a different test, the integral test, to figure out if our infinite series converges or diverges. So we have the integral test, which requires three conditions: that the function f is positive, continuous, and decreasing. And we do have to state that when we're using this test, that to say like, oh, it's legal for us to use the integral test, okay? And it has to be for our bound that we're using. So it has to be positive, continuous, and decreasing for our bound. So we're going to say that the series, the sum of from terms n equals 1 to infinity of our function a, or of the rule a sub n, then if that summation and the integral from the same bound 1 to infinity of f of x, which is really just our a sub n, just rewritten in terms of x, if that converges, then the summation is also going to converge. If it diverges, then the summation will also diverge. And we know this, we can use this test because basically what we're looking at with a summation, I think about it as an infinite Riemann sum. So if I take the geometric look at the area under the curve, I'm like, oh, this value here, I'm going to make a rectangle, and I'm going to add up all these different little rectangles under the curve. So I know if the black curve here diverges, then the Riemann sum, well, what I think about as the sum, the summation or the series diverges, then the sum will also diverge. So that the integral diverges, the sum diverges. If the integral converges, then the series or the sum converges. Okay, so we're going to use this test. We're going to use the integral test to determine convergence. Okay. So for the first one, the sum from terms n equals 1 to infinity of n over n squared plus 1. So basically this n squared plus 1, that is a sub n. So we need to say that a sub n is equal to f of, well, we're going to say that f of x is equal to x over x squared plus 1. It's just a sub n, but written in terms of x. And we have to state that we can use the integral test. So the conditions are that f is, and we're going to check, is it positive? Are the terms decreasing? And is it continuous? Okay, so I'm just going to think about the what this looks like. X over x squared plus 1. If I plug in some values, so I'm going to plug in like f of 1, because that's my first value, I get 1 over 1 squared plus 1. F of 2 would be 2 over 2 squared plus 1. F of 3 is 3 over 3 squared plus 1, and I'll go ahead and simplify those. So 1 over 2, 2 over 5, and 3 over 10. So I can see as we move, as the x's increase, the values are all positive outputs. We are decreasing, and nothing in the denominator is going to make us have a discontinuity. So we fulfilled all of our requirements to use the integral test. So now we can set up our integral. So I'm going to say the integral from 1 to infinity, because that's our bounds, of f of x, which is x over x squared plus 1, is equal to dx, or equals dx. Okay, and we know that this equals the limit, as I'm going to use b approaches infinity, of 1 to b of x over x squared plus 1 dx. I am going to use a u substitution, the denominator of 1 of x squared plus 1. So du is equal to dx. Wow. Du is equal to 2x dx, and then divide by the derivative to give me dx is equal to du over 2x. Now I have the limit as b approaches infinity, the integral of 1 to b, of x over u du over 2x. And my x is canceled. So I end up with the limit as b approaches infinity of 1/2 times the ln of u, the ln of the absolute value of u. So I am going to just replace u squared plus 1 with the terms of plugging in 1 to b. I made a mistake here. So because I changed in the second to last step here, I changed my bounds. I need to change my bounds to be u of b and u of 1 since I changed my equation in terms of u. Okay. All right. Now I switch back into x so I can use the bounds 1 to b. I am going to substitute the b value, the bounds. So 1/2 times the ln of the absolute value of b squared plus 1 minus 1/2 times the ln of the absolute value of 1 squared plus 1. Okay, I put that in parentheses so I know I'm taking the limit of the whole thing. All right, so now I can go ahead and substitute my infinity squared plus 1. The plus 1 really doesn't do anything. Minus 1/2 times ln of 2. Okay, so what I get is ln of infinity is just infinity because the curve of ln just increases. So slowly, but it increases. So minus a value, half ln. Let me try to do that right. 1/2 ln of 2, which is just a number. But since one of our limits goes to infinity, the series diverges by the integral test because the integral of 1 to infinity of the function f of x, which was x over x squared plus 1 dx, diverges. So remember, if the integral diverges, then the limit diverges. Okay, so if it's easy to take the integral test is nice because it tells us if the series is going to diverge or converge, not just diverge, like the nth term test. All right, so we have to test. We're going to say f of x is equal to 1 over x squared plus 1. And is f continuous, positive, and decreasing? And I notice that it's always going to be positive because I'm only substituting n values that are positive. It is continuous because the denominator is, the variable is being squared, so there's nothing in the denominator that will give me a vertical asymptote or a hole. And we have 1 over a number that continues to grow in the denominator, so we are going to decrease. So we can go ahead and set this up as the integral from 1 to infinity of 1 over x squared plus 1 dx. So improper integral gives me the limit as b approaches infinity of 1 to b of 1 over x squared plus 1 dx. I immediately recognize this integral as the arctan. So this is the limit as b approaches infinity of arctan. And my u is equal to x and my a is equal to 1. So it's arctan of x. And my bounds are 1 to b. Time to substitute. I have the limit as b approaches infinity of arctan of b minus the arctan of 1. Go ahead and plug in infinity. So arctan infinity minus arctan of 1. And remember, arctan looks like this, where we are approaching pi over 2 as x goes to infinity. And when is the tangent ratio 1? That's when the angle is pi over 4. So we're going to subtract pi over 4. So I end up with 1/2 minus pi. 1/2 minus 1/4 is 1/4 pi. So the series converges by the integral test because the integral 1 to infinity of 1 over x squared plus 1 dx converges. All right, last example for the integral test, and then we'll look at another test after this. There's so many. All right, so we're going to look at the series, the sum from n equals 1 to infinity of 1 over n ln of n. So my function that I'm going to evaluate is 1 over x ln of x, and the function of f of x is, we're going to check to see if it's continuous, positive, so it's definitely positive, and if it decreases. So it definitely decreases because the number in the denominator is just going to be getting larger and larger and larger because x increases and ln increases. They're positive because we're only substituting in positive values, and positive values greater than 1. So remember, ln of x crosses the x-axis at x equals 1, so we're going to have positive outputs after x equals 1. And then we also have to be continuous. Oh, this is the problem. I wrote this problem down wrong. We're going to start at n equals 2. So when n equals 2, normally we would be n cannot equal 1, nor can n cannot equal 0, otherwise we'll be undefined. But because we're starting with the value of n equals 2, then we don't have to worry about the discontinuity at n equals 1 and n equals 0. So this function is continuous as well from 2 to infinity. Okay, so we're going to set this up as the integral of 2 to infinity of 1 over x ln of x dx. We have to use our improper integral rules. So as b goes to infinity, of 2 to b, 1 over x ln of x dx. I'm going to make my u equal to the ln of x because I know that the derivative of u is 1 over x dx. So when I divide by the derivative, I get x du. So I have the limit as b approaches infinity of from 2 to b of 1 over x times u. Oh, we need to change these to u of b and u of 2. Okay, because we changed into in terms of u. So we have du times x. So my x's are going to cancel, leaving me with the limit as b approaches infinity of u of b, u of 2 to u of b of 1 over u du. I recognize that integral as the ln of the absolute value of u, which I will replace with the ln of x because that's what u was. Okay. The ln of x, I don't need the absolute value because the ln of x was just a normal ln of x. Okay. That's what u was. And we're evaluating from 2 to b. We switch back into the x bounds. Okay. So we have the limit as b approaches infinity of ln of the absolute value of the ln of b minus, minus ln of the absolute value of the ln of 2. Okay, substitute in the infinity. Ln of the absolute value of ln of infinity minus the ln of the ln of 2. And what I see here is that we're going to get infinity. And then, so again, the ln of infinity is infinity minus some value that I'm not going to evaluate. Okay. So I see that the series diverges by integral test because the integral of 2 to infinity of 1 over x ln of x dx diverges. So the series diverges as well.